Ladies and gentlemen, our next speaker, Bunnie Huang, is a hacker par excellence. If you don't know his work, you should, but this is one of those times where I'm half tempted to say our next speaker needs no introduction, drop the mic and walk off. But the range of hacking activities that Bunnie's been in through the years is fantastic. From reverse engineering to kind of cryptography and privacy in computing to Shenzhen advocacy and kind of bringing us closer to where the parts are getting made. Can't say enough good. So I'm going to let you look into his next project here. This is actually a stellar project, Iris. He's looking into silicon with infrared, making inspection technologies that used to be completely unaffordable, affordable and like near to the normal hacker. So without further ado, please take it away, Bunnie.
Yep, thanks a bunch. Thanks for the introduction. Thanks for reminding me about the Shenzhen stuff. Actually, I made a book about Shenzhen. It's open source, and then there's a new maintainer, and she sent me like a whole pile of these. So I always carry them with me, and I'll just put them here. If people want a copy, just grab it. It is yours. Yeah, it's great. It's great to have a new maintainer for the book. It's up to date, and she's been killing it, Naomi. So, yeah, thanks for giving me a bit of your time. I guess the slides are still not on the screen yet, but I can talk a little bit. Coming back to silicon and working on silicon is a kind of coming full circle for me. When I graduated college and started my professional life, I actually was a chip designer. And in college, I had the privilege of like designing transistors down to the level of like computing the voltages for ion implantation and carrying the wafers to the furnace, and then hydrofluoric acid safety like measures and all that sort of stuff. And I initially got into chip design as a professional. And the thing is, like, the chip design culture, I didn't know at the time, is incredibly toxic, right? It's all about gatekeeping, and it's very, very close source. I got frustrated with it, and then that started me on this whole arc of going to Shenzhen, doing manufacturing, promoting open source, these sorts of things. And so now, I actually just recently turned 50, and I'm kind of reflecting where I want to be in my career, and I'm like, I want to go back to chips, but I want to go back on my own terms, right? I want to do chips, I want them to be open, I want to try and figure out how to solve a bunch of these problems. And one of my philosophies is that engineering and hacking are two sides of the same coin. So if you're going to build chips and you want to make chips, you also need to be able to look at, observe chips. And so in addition to, if all goes well, by around this time next year, I can talk to you about my experiences taping out a chip in TSMC 22, which are just hopefully masking out soon. The other half of it is trying to come up with tools to help us look at these chips, right? And so this talk is about seeing through silicon with a technique that I dub Iris Infrared In-Situ. So basically the technique, it's a way of inspecting chips that are already on circuit boards. So looking at chips is a thing we can do. We can put them in SEMs and whatever it is, but you have to pull them off the board. And after you do that, the chip doesn't work anymore. So this here is kind of like the most compact, like 5-second loop I can come up. That's a chip on an iPhone motherboard. When you see it turn sort of that purplish color, that's the infrared illuminators coming on. And I'm taking the light, and you can swing across the chip, and you can kind of see as it goes into this color here, you can see there's actually some circuits I bring into focus. And then that black and white image that comes out is actually like a high-resolution stitched image of the chip. So it works like that. It's almost like magic, right? It only works on certain types of chips. The short answer is it's the shiny ones. So they're called wafer-level chip sale packages or flip chip BGAs. They need to have no paint on the back or films applied for this to work. You can scrape them off if they're on there. And the other kind of caveat is it needs to be a P- doped substrate. So this is like the base silicon wafer itself has to be a very lightly doped silicon wafer. The reason why this matters is that Intel uses a very heavily doped wafer, and so Intel chips don't image as well with this. You have to use a laser to get the intensity, which like increases the cost a little bit. You can do it, but it's a little bit harder with an Intel chip. It doesn't work with chips in plastic packages. So yeah, unfortunately, probably most of the chips on your badge or whatever it is already in a plastic package. It won't work with them. But Turns out this style of package is very important for essentially every mobile phone uses it. A very large portion of chips in the supply chain use this, and a lot of manufacturers offer chips in this format. So if you're designing something for inspectability, you can just pick it and use it. So how it works. Silicon is transparent to infrared light. This is a graph of the sort of the depth at which light will penetrate silicon versus wavelength. In visible light, it barely goes through silicon at all, which is why it looks, opaque and silvery. Around 1,000 nanometers or so, the light will start to penetrate the wafer at a depth of like about a millimeter or so, which happens to be the thickness of a chip, which is perfect. And then, of course, as you go on, it gets very, very, very transparent. It's like the best glass you've ever seen. And the other reason why this is actually kind of possible and accessible is that some standard CMOS sensors are just sensitive to infrared off the shelf. So a lot of those surveillance cameras you see going on, big market for those, they're infrared enhanced because people want them to work at night. And so if you look at the spectrum of these sensors, you can see, on the left-hand side is the visible, there's the red, the green, and the blue filters. What happens is they tune the color filter gels over the CMOS sensors so that as you go to the infrared, they become perfectly transparent. So all three sensors start to work in unison, sense the infrared, and the efficiency of the sensor drops. So you can see that the actual responsivity goes down to about 0.4, 0.3, but all three sensors are working together. So you have actually 3 times the light collection area. So at the end of the day, you basically have a night vision camera that works with a regular CMOS camera. Put that all together, you have this technique called IRIS. So it's basically inspection of chips from the backside after they've been assembled into a product. This is sort of like if I were to cross-section a circuit board. On the bottom is the PCB. On the top is a very, very, very zoomed-in version of the chip. And you can see that where the metal and the solder balls are relative to each other and where the camera and the light are. So why is backside imaging in particularly interesting? Again, this is a cross-section of the chip. This time, the backside is on the bottom and the front side is on the top. And it turns out that when you look at a chip from the backside, you are actually looking at the transistors. Again, a chip is a big sandwich of many, many, many different metal layers, so it will block light. You can't go all the way through to the top. But if you had 2 sides to look at, the top side or the back side is the more interesting side from the verification standpoint, because that actually has a correlation to the transistors on the chip. If the wires aren't there, the transistors are hooked up, they don't do anything, so you can say for sure this circuit exists or not. And so, for example, this is a backside image of a chip here. I take a little zoom in, and those squares, that area of 9 squares, each of those is a transistor that's part of probably a band gap or something like that. They're laid out in 9 separate segments to balance off process issues, whatever it is, right? So you can actually see the individual transistors. There are many ways to implement it. It's very important for me for the technology to be accessible. Like, people need to be able to do it at home in their privacy. They don't have to buy a big machine or go to a centralized authority. So there's a version for less than 300 euros or so, or if you have the equipment already, it's basically free. You can do it, basically, you take any lab camera, pull off the infrared filter on it, and it basically just works. It's pretty amazing. So I have a video that shows you how to do it, how to mod a camera to do this. Get a little monocular zoom objective. And it turns out, actually, the cheaper parts work better because the more expensive ones have anti-reflective coating that are tuned for optical, like visible wavelengths. If you get the really, really, really cheap ones off of AliExpress, they don't have the coating. They actually work better for this. So, actually, the cheaper parts work better. And then I have another version about a few thousand euros, but it's fully automated. So we can do repeatable measurements, high-resolution measurements of devices. So the manual adjustment setup, I have a little GIF loop here showing what it looks like. There's a little chip from an iPhone motherboard. Normally, it would be silvery, when you look at it. And as I swing the light across it, you can see actually the transistors kind of appear just above the Apple logo. Do you see that little bank on top? That's actually a switching regulator chip, and each of those little white kind of squares you see actually consist of a number of small lines, and they are the output drivers for the buck regulator, for example. So you can just see it through the back side of the chip. So you can do this at home. This particular example here is a CMOS, a standard Sony Alpha 5000 off the shelf, but then you pull out the infrared blocking sensor, and it works. That's a phenomenal sensor, actually. You get really good high-resolution photos out of it. So you have an old camera laying around, you can pull out the IR blocking sensor and just repurpose it for this. It's good for end-user verification setup, so if you have something you want to look at, it's low cost, a little more effort, a little fussy to set up. Vibrations are a problem at these resolutions, but you know, if you're going to use it rarely, I think it's a suitable device. The fully automated version has like this CNC-controlled light source on it. You know, moves in 3 dimensions. It can adjust, you know, where the lights come from. This is good. You know, it has 10 micron precision repeatability for the imaging. It's good if you want to make reference images, or if you have a higher throughput issue, like you're buying servers, you want to do 100% inspection on all of them. This is the sort of thing you might get to throw the motherboards in, have a look at it. The platform itself that I use for this is actually open source platform. It's nominally for all kinds of 3D motion stuff. Obviously, 3D printing is like the killer app for any of these types of things. But it's called the Jubilee, and it's actually really interesting because it's kind of designed to be extendable for applications like this. So as a tool changer, so instead of putting the print head on, I can put the microscope on and move it around, and has extensible firmware. So you can check out the more about the core platform there. The actual microscope core itself is a thing that I built from parts, and so I thought microscopes were really hard and expensive. Like I was like, oh, it's a Toyo near infrared, $14,000. This is going to be really impossible. Oh my God, it's going to be terrible. Turns out a microscope is just an objective and a lens. It's like, it's that simple. I was like, really? Like I built essentially the same thing that you would pay $14,000 for from In-Situ for like $1,000. The objective is expensive bit. The tube lens is about $200 off of Thorlabs, and it's just tubes, like at the right length. You have to know a little bit of math to tune the tubes, but you basically then just, that's a microscope, you're done. And then around it, I put a couple of actuators to go ahead and position the light, move it up and down to get the light source. And the reason why the light source positioning is interesting is this is a video of actually a light that's imaging a chip, and as the video goes, the light source is rotating about the axis of the microscope. And so it turns out, people say, oh, but wait, 1,000 nanometers is huge for a chip. Like transistors are, you know, in nanometer range. Well, this is true, but it turns out what you have is you essentially have a hologram. The chip is like a diffraction, and so the angle that you look at it changes what you see, right? And so you can actually get more information about the construction of the chip if you can adjust the position of the light instantly on the chip. And so as we rotate it around, we can sort of see the different logic cells will actually have a different reflectance as you move it around. And so with sort of a time domain measurement on this, you can actually get kind of sub-wavelength features out of the chip, which is why I put effort into build like this rotating light head automatically. Another cool little thing is like focusing is really hard at these situations. Like you have mechanical stuff can only really repeatable to about 10 microns, which is outside the focal depth of something, you know, a lens at this quality. And so I had to build a fine focus stage. Back then it was $200. I mean, supply chain stuff, it's a little more than that going if you were to buy the parts today, depending on what region you're in. But yeah, I originally thought I would have to spend thousands of dollars for one of these like piezoelectric fine focus stages. Read some books about, you know, this is one of my favorite things where it's like very rare do you find a situation where you can take math and map it onto something physical, right? And so what the trick here is that if you want to locate an object precisely in three-dimensional space, the math says you need 6 points. 6 points fully defines an object, no more, no less. If you have more than 6 points, this is what's called over-constrained. And then, so for example, when you take the stage off, you have more than 6 points of contact. Which point are you using? It will shift around every single time. So if you want to create a very repeatable coupling for a stage, all you need is to take your aluminum stage and cut a V-shaped groove in it. That creates a plane. And you made it against a glass bead. So these are crafting beads that you can just buy off of Amazon for, like, you know, if you want to do like raindrops or whatever it is on like a little collage. These are literally what I bought. And when you put those glass beads inside those V-grooves at 3 spots, you have 6 points. And the math works out so that you can take that stage off, do what you want, put it back on, and it goes right back to like nanometer precision. It's the math and physics just works out. It's so cool. I always thought these things were super hard, but it turns out if with these exactly constrained designs, you can just do it yourself, right? The whole thing, open source. So if you are interested in looking at it, bunnie.org/iris is a link tree for a lot of the docs and whatever it is. I have blog posts that tries to go into everything. Very quickly, go over some examples. Almost out of time. What can you do? You can see with it. There's a link here for John Max's website called siliconprawn.org. I took a few images that you can just download and look at high resolution, poke around, have a look at it. A kind of more relevant stuff, the Sky 130 processor, I think Matt Van actually sent me some samples and I was imaging them and all that sort of stuff. This is what that looks like using Iris backside imaging. You can actually, and because I have the GDS2, I can actually overlay what the gates are. So they actually each logic cell is about 30 pixels or something like this on the side. Gives you an idea of what we can't actually see the individual parts of the transistor, but the logic gates themselves are morphologically different using this technique at 130 nanometers. Giving a little more intuition about the block sizes, because a lot of people haven't seen chips. This is a 65 nanometer node chip. I'm just estimating. I don't actually have design source for this, so it's all just based on guesses, counting parts and whatever it is. 3.8 millimeters is the vertical axis. A small CPU core would be like that region there that I have highlighted out. This is actually, I think, audio codec. So it has a little core that controls the DSP and whatever is going on. And then that little corner there I have is about 4 kilobytes, 8 kilobytes of RAM, right? So that kind of gives you an idea of how big these things look like at the end of the day. And if we were to go ahead and zoom in, everything is so cool when you look at these laid out chip designs. They have these round spots. It's almost like mold growing, very organic. And it turns out just, when you're laying out chips, you want to have your timing closure. If you have a flip-flop, you laying the gates out around in a circle around it so it all kinds of, the wiring delays are balanced. One of these little sort of clusters can hold about 100 logic gates, roughly. If you were to tile it perfectly, it turns out no one ever does, so in practice they hold 10 or 20 logic gates. As a hardware engineer, I found I have to write actually mostly software, so there's tons and tons of software that goes with this for commuting the autofocus, whatever it is. When you get a whole bunch of images raw, this gives you an idea of, it's not perfectly aligned. Those are the machine tolerances. You can see the logos are kind of messed up. There's a semi-automated image stitching, automated stitcher that I wrote as well that you can just download and use. And yeah, so go check it out. I just want to sort of tell you guys about one, like I said, is one half of the coin. I'm also working on making chips as well, but that's still in the oven, and hopefully next year I'll have some more stories and war stories to tell about it. With any luck, the lawyers don't go back on their word. At least part of it will be open source, right? But I'll believe it when I see them allowing me to push the stuff up. We're still sort of arguing over the details. Yeah, and so the work is actually all open source, funded by NLNet and my GitHub sponsors. So really big shout out to everyone who makes it possible for me to do stuff like this and actually put it out in the open, let people use it. So it's not honestly, when I first was telling some of my friends about this, they said, oh, you have to start a company around this and get VC and it's going to be so amazing. I'm like, but then the problem is I'm going to have this incentive to lock it up and make money off of it because I have to return to the investors. And so it's very important for me to make sure that this type of stuff is in the hands so people like you can just go ahead and build it, do it yourself, improve it, share it, put it out in the community. So thanks for everyone for listening in. Have a good lunch.
Thanks very much. Super quick announcement before lunch happens, and then off you go. We have 2 colored tickets, and one of them is for Indian food, that's the green one, and one is for East African food, that's the red one. You can have either for lunch and for dinner, but you have to choose which one you do first. Good luck. Have fun out there.